Hi, Friends of the Sun. This is a weekly online reading group that's held on Zoom, and authors present their papers here. And usually we have stuff about building structure into machine learning models. And today we talk about chirality for message passing neural networks. So let's go.
So, hi, I'm Peter, Piotr, from Jagiellonian University, from Poland, from the machine learning group, which logo you can see here. Okay. And today I'm going to talk about our latest paper called ChiENN, which is about embracing molecular chirality with graph neural networks. And this paper was created obviously with collaboration with some people. They were Michał Koziarski, Jacek Tabor, and Marek Śmieja, which are super colleagues, supervisors, and super advisors of me. And the paper is about, two things happen in the paper. First, we define order-sensitive message passing that can capture chirality in, let's say, a wide range of chiral-sensitive tasks, graph tasks. And then we use that order-sensitive message passing to design a chiral-aware edge neural network called ChiENN, which is aware of molecular chirality and achieves pretty good results on chiral-sensitive tasks for molecular property prediction. And the table of content is that we are going to talk about chirality, and then about related works, and then about our method and results. Okay, so chirality. Chirality is a kind of asymmetry in math, and an object is called chiral when its reflection cannot be translated or rotated back to the original object. And here we see an example of a chiral graph, 2D graph, and its mirror image. And we observe that by any rotation or translation, we cannot align those two graphs together. So they're kind of different. I hope it's clear. And the same things happen for molecules. In molecules, we usually talk about tetrahedral chirality. And a chiral center in a molecule is a carbon atom with 4 different constituents. And a molecule with at least one chiral center is chiral because you can mirror image that molecule. And here we have an example of chiral molecule, cartoon 1, which on the right side you have its mirror image, which again cannot be rotated and translated back to the original one. Okay, and in molecular chirality, maybe strange things happens because we are not really interested in specific angles in molecular chirality. So it's like when you have this seemingly chiral molecule, yes, and its mirror image, it cannot be rotated and translated back to each other. However, they are not called chiral. I guess that's because molecules have some degree of freedom, and the bonds can, these bonds can, in some sense, straighten up, yes, because it's energetically feasible for them. So it's like we are not really interested in that kind of almost chirality. We are not interested in angles, meaning that the core of molecular chirality, I believe, is the arrangement of the bond, the order of the bond. It probably will make more sense when we talk about the explicit tagging of molecules. Okay, so is everything clear for that moment? At that point? Okay, great. And now, why are we concerned with chirality? So let's make a definition. A molecule, chiral molecule, mirror imaged is an enantiomer. And so a mirror image of a molecule is called enantiomer, I guess. Enantiomer, probably. And enantiomers share many properties, physical ones like boiling points, etc. However, they can behave very differently in the biological context. For example, in human body, when you have a lot of proteins that are chiral, like left and right hands, and then it really matters. And we have a lot of really sad examples or terrifying examples of chiral drugs that were not used properly. And here we have a cartoon 1, which is not so terrifying. I mean, one molecule can save the world, and the other one gives you a headache. They're pretty much the same, but they're mirror image, and the mode of action is very different for those molecules. Okay, so for that reason, I believe that capturing chirality is kind of critical in the context of drug design, and it should be incorporated in early phases of this. Especially where the molecules are tested in silico for some kind of molecular properties. And the problem is that most of the methods, or let's say the vanilla message passing or graph neural networks, are unable to capture chirality by design. So it's like we would like to have a GNN, graph neural network, that actually captures the chirality, which more or less means that we want it to be able to output different properties, different scalars, whatever, for enantiomers, for chiral molecules that are somehow mirror imaged. Okay, and obviously we are not the first one that it's kind of interesting and vital. And there are a bunch of methods that actually can capture chirality in some sense. And the first one, probably white one, is actually P3 equivalent GNNs can capture chirality. I mean, they are equivalent with respect to reflections. However, it's like they're rather suited for predicting tensors or vectors, not predicting scalars. And as far as I know, they are they're not working very well for predicting molecular properties like the scalar ones. The other group of methods that can capture chirality are 3D GNNs that use torsion angles. Yes, the torsion angles are angles between the planes. It's not really important what is it. The point is that the problem is that they are conformation sensitive. So it's like when you put different conformation to that model, it will output somehow different prediction, and it's kind of annoying in the context of molecular property prediction. And they also evidenced not to work very well for the molecular property prediction. Okay, yes, there's a question.
Yeah, I'd like to ask, like, what are the inconveniences just having a chirality flag in the features of the atoms? And why do you need a method that understands chirality more than just having a chiral flag?
I will talk about it a little bit later. I mean, because this method, when you add a chiral flag, I call it here explicit tagging of a chiral center, and it will be discussed more detailed, and then we can talk about that, why it's not sufficient. Yeah, but
okay, perfect.
ask me a question. Okay, so then you have a method which is kind of related to our method. It's called tetra-DMPNN. I mean, I don't know the name of the paper. It's referenced in the presentation, so we can look then on that. It has also some drawbacks. It's computationally expensive and only limited to molecules because it also uses the chiral tag. And the second one, which we talked just a while ago, is explicit tagging of a chiral center. But this one is also not very expressive and only limited to molecules. We will talk about this later. And here we have the last one, and definitely not least, is Cairo. I believe it's called Cairo. It was presented during that, in your reading group, I guess. And it's current state-of-the-art method for chiral-aware tasks in molecular property prediction. It's really nice. I mean, it's mathematically, let's say, beautiful. However, it's kind of complicated and most limited to molecules. I mean, I don't see more drawbacks of that method. However, it's kind of different to ours, so why not to have two? Okay. And what we have done by introducing our model, first we all the methods have their limitation, and we overcame them. Moreover, we proposed a more general approach to chirality, which is not only designed for molecules, but for, I believe, much more chiral-sensitive graph tasks. And moreover, we outperform this aforementioned Chiral by a quite significant margin. Okay, so let's talk about the explicit tagging of a chiral center. It's important for our paper because our method is slightly inspired by this scheme in some sense. And moreover, the explicit tagging is the simplest and the most commonly used method of incorporating chirality. Yeah, so why not to know how it works? And it works like for every chiral center we assign a label for that, like for example clockwise, counterclockwise CCW or clockwise tag. And this tag is computed as follows. So first of all, we have a tetrahedron. We have this chiral center. We enumerate all the constituents using some arbitrary algorithm that simply assigns some number to all the constituents. And then we choose, and then we distinguish one constituent that has the, let's say, the highest assigned value. And because we distinguish the constituent, we also distinguish the, let's say, the directed bond, C and H. And right now we can intuitively look down from the distinguished constituent from that H and draw a counterclockwise or clockwise circle around the rest of the constituents. Okay, so it's like this constituent has numbers 0, 1, 2. So let's draw a counterclockwise circle, and those constituents has order 0, 1, 2. So let's draw the opposite tag.
Can you repeat how the numbering is chosen?
Sorry, is there any repeat?
Can you repeat how the numbering is chosen?
No, it's like this algorithm is, I believe it's supposed to return distinct number for every constituent. And it's like, I mean, the definition of a chiral center is that every constituent is distinct, is different. So you can somehow make an order of them because they are not the same.
Yeah, and how do you make your order in practice? Do you like get the string and order them alphabetically, or what do you do?
That's a tough question. I cannot answer because I don't really know. I mean, there are at least two methods how to do that. One is, I guess, I mean, both are probably kind of complicated and arbitrary. But I don't know how they work, to be honest. I mean, it's like you have an algorithm that can enumerate the constituents, and for us, it's, I believe, for me at least, it's sufficient.
Yeah.
However, the fact that it's an algorithm that enumerates the stuff slightly complicates things because explicit tagging distinguishes enantiomers. Yes, it's like it always returns different tag for different chiral centers or mirror image chiral centers in the molecule. So it distinguishes the enantiomer, but it's kind of arbitrary because it's like the fact that one tag is counterclockwise and the second one is clockwise doesn't mean a lot. And it's like because you are using an algorithm to enumerate these constituents. I mean, you can find some strange and stupid corner cases when slight change in some constituent will drastically change the chiral tag enumeration. So it's like you can distinguish enantiomers using chiral tags, but it's like kind of maybe not really strict argument that they're not very expressive. And probably the better argument is that, I mean, the results shows that it's not really good in most of the chiral tasks. It's like, There is some intuitive kind of philosophical argument why it's not so expressive, but no, I believe that numbers are slightly better. Okay, so any questions so far? Okay, so let's talk about our method. So we basically do three things here in our method. First, we define a circular neighbors order of a neighbors of a node, central node, that capture the chirality for 2D graphs. Then we design a kind of general message passing scheme which is order sensitive. So it can distinguish between different orders. We'll define orders later. And then we apply this order sensitive scheme, message passing scheme, to molecules. And the result is our method, our edge neural network. And the important thing is that this transformation from a 3D molecular graph to kind of 2D molecular graph uses the distinguish an edge trick from this explicit tagging scheme. So it's like it's good to have it in memory. Okay, so let's define the neighbors order. So here we have a graph embedded in 3D space, 2D space, and we see that we have a graph and a mirror in, and we can simply enumerate the neighbors. I mean, change our direction, for example, clockwise manner, and then enumerate the neighbors in clockwise manner. And here we obtain two tuples that are different. Yeah, it's quite kind of straightforward. And the order, the point is that the enumeration can start at any point. So we want this order to be kind of shift equivalent. So we can define the order of a neighbors as a set of shift equivalent, tuples or neighbors enumerations. Yeah, so like all these tuples are basically the same. Okay, great. And right now we have defined the order, and now we want to have order sensitive message passing. And what it means, first of all, we want this message passing to be shift invariant. Okay, so we want all the equivalent order to be the same, and then we want to the different orders that comes from the mirror images. We want them to be not equal. Yeah. Okay. So first, let's talk about the shift invariance. Okay, and first of all, I guess you all know the vanilla, let's say vanilla message passing scheme, which is permutation invariant with respect to the nodes. And it occurs that it can be written in this form. Yes, when you have, let's call it message function that takes the central node, the neighbor node, and then you have a summation of that messages, and some whatever function C, I guess, rho, it's wrong. Okay. And here we have another example of such a network where we have very straightforward row function. Yes, and we have a C function that takes only the neighbor. So it basically looks like this. Yes. So here are the messages, and they are summed, and that's all what is happening. However, we want to loosen this permutation invariance and enforce the shift invariance. And what it means is like if we want our message passing to be shift invariant with respect to the neighbor's order, which we defined previously, this shift equivalent order, then your message passing can be written as the following. So here we have an extended version of message passing when we not only takes the one neighbor, but we take a sequence of the neighbors in order, and those neighbors are shifted by p. Probably it's better when I show you an example. Okay, so here we have an example of such function. Again, a very simple X embedding. And here we have a psi which is actually constrained to be k-ary. Yeah, so it only takes k neighbors, and those neighbors, and the p is a shift argument, yes, in the permutation. So this in this is addition is kind of modulo d. Okay, so here we have an example. For p equals 0, we take two neighbors in order. Yes, we embed them. Then we shift by 1. Then we have those neighbors. We embed them, and then we shift by 2, and we have those neighbors and embed them. Yeah, so it's kind of we've make the message passing slightly more general. Yeah, and we enforces it to be shift invariant. Yes.
And k can be anything, right? So you could also take 3.
Yes.
Well, it can't be 1.
It can't be 1. It can be anything. Yes.
Well, if it's 1, then we no longer have the other property. You still have
Yes.
shift invariant, but you don't have the, what did you call it?
I mean, when k equal 1, we have the casual message passing. It's like it's permutation invariant by definition.
Yes, but if you take 1, then you no longer want to be permutation invariant, right? So if you take k to be 1, then you would be permutation invariant.
Then it wouldn't be, yes.
No, if your k is 1, then it would be permutation invariant, right?
Okay, yeah, sorry, yeah, it would be, yes. But it also would be, yeah, it would be shifting invariant permutation invariant. Sorry, I thought that you were talking about shift invariant, sorry. Yeah, right.
We don't want it to be permutation invariant.
True. That's true. And to make our life simpler, let's stick to some instance of that shift invariant message passing. We are using, this instance along the paper, and this is basically what Hannes said, that it's like this message passing still can be permutation invariant, but it may also not be. So we want to ensure that it's not permutation invariant. Yes. So it's like it's only shift invariant, because the different permutation are different permutations that are not shifts of the same permutation are different images of or are mirror images of the chiral center or whatever. Okay, so let's talk about the order sensitiveness. And so we want to design this psi so that we know that it can learn to distinguish between enantiomers, between the different permutations. And the first thing is that k must be larger than 1, and this is exactly what Hans said, that when you take k equal 1, we will have standard message passing, which is permutation invariant. Moreover, psi cannot be, I believe it's psi, cannot be linear. And the reason is that the linear embedding will cancel out in those, even for different permutations, so the results will be the same. However, we can use the magic of universal approximation theory and put and make and let the psi be MLP, yes, and then we can somehow believe that this MLP can actually learn how to distinguish between different permutations. Okay, so now we enforce that our method is able to learn how to distinguish between graph and its mirror image. Okay, and here we have a final form, which is basically we write here an example of MLP, and we simply stack the neighbors it's not stack. We simply concatenate the neighbors and put it to the MLP. Yeah, so it's convenient to have a fixed K for that reason, which is not really big. And what is probably interesting is that our method not only captures chirality, but also something more. Namely, here we have two graphs that are not, let's say, they are not mirror images of themselves. Yes, I mean they are 2D graphs, because this part is pretty much the same. This one is the upper one is mirror imaged, but still our method can distinguish between those two graphs because they have different permutations of the neighbors here. So it's probably good. Okay, so we have a model that a message passing scheme that can be used for 2D graphs. However, it's not so, at least to me, it's not so trivial to define an order for 3D graphs, like the neighbor order, even for a simple tetrahedron. However, it starts to be simple when we distinguish an edge. Yes, as in the explicit tagging scheme, we distinguish one edge, and right now we can draw a plane that is perpendicular to that edge. We can choose some direction, I mean, as before, as in 2D case, and order the constituents like this. Yeah, so we basically can, when we distinguish an edge in a molecule, we can reduce this this 3D case to 2D case, which we can deal with. Okay, and the question is how to distinguish an edge in a graph. And probably the most simple thing is to simply think, because message passing in some sense distinguishes a node, because we pass the messages to some node, central node. So in some sense we can think that when we swap edges and nodes, so when we passes the messages not to nodes but to edges, then an edge will be distinguished. Yes. So what we do, we from this graph we build a directed graph when each bond is a each bond makes up two directed edges, and now we treat that edge, that gold edge as that central edge, and here we have all the incoming nodes, or all the incoming edges are the neighbors of that edge, the gold edge. And so we somehow we simply transform a graph by swapping the edges and nodes in some sense. I believe it's called a dual graph, but not sure. Okay, and there's obviously a problem with that approach because some edges may be parallel to the central edge here. Yes, for example, the edge that comes from H to C, and it's not really clear how to put that edge into the order of that of these nodes that are projected to the to the plane perpendicular to that edge. So we can simply make a set of that parallel edges and somehow order them. However, in molecules, it's not necessary because there will be at most, or in our data set that we are interested of, there was only a one edge that was parallel to that central edge. So we can simply embed it outside the neighbors. It's like we are not treating this edge as a neighbor of that edge. We are treating it somehow distinctly. Okay, everything is clear here, more or less.
Sorry, yeah. Can you just maybe tell us how this can be generalized to larger graphs and like even to chirality centers that have like up to 10 nodes. If the number of those parallel edges would grow, how difficult would it be to select a canonical ordering?
Okay, so I believe that probably the simplest solution will be to split the neighbors into groups. The neighbors that are parallel, like this one, and somehow order them. For example, by distance to that edge or whatever. And the rest of the edges won't be parallel. So you can project them to this 3D plane and order them. And I believe that when so you can do that. You can also have edges that are parallel in maybe that was your question, because some edges may be parallel not to that edge but to each other here. Maybe that was what you asked about. Yeah, so we can
yes,
have,
kind of.
okay. So so when we project these edges to this plane here, then some of them may actually be at the same point, okay? Because you can have an edge right here, which will actually be aligned with that edge on this projected plane. But then I believe you can still sort them somehow, because then you can you can make another projection which is parallel to that edge. Yes. So you will have some order of the coordinates of the edges, and you can sort them using those coordinates.
But if you then so I'm just trying to understand how sensitive is the network to the change of this canonical ordering. So if we just then do another canonical ordering and retrain the neural network, then like I suppose that it will perform similarly.
If you change canonical order,
so
okay, I guess that when you have this simple case when there are no parallel edges to that neighbors, I believe then I mean, you can swap the direction of that numbering. But I believe that it will influence the performance.
Okay, thank you.
Okay. Okay, so are there any different questions? Okay, and as a result, we obtained let's say chiral-aware layer that can be stacked and used as a standalone model, or it can be appended to some existing GNN. It's because when this transformation from a graph to a dual graph basically change nothing. I mean, it's like still we have a graph that we can probably perform all the operations on using some other GNN. So it's so we can use that model in two modes. Okay, and here we have a short list of tasks that are chiral-aware. And the first one is kind of a toy task. When you want to predict the chiral attack, it's called RS. It's I believe it's the same as control clockwise and clockwise. Okay, so we want to classify a molecule and say whether it has this stack or this stack. Moreover, we have an enantiomer ranking, which is a task copied from the chiral paper. And it basically consists of pairs of enantiomers, yes, that were binded I believe, in a simulation to some chiral protein, and they have different binding affinities, kind of significantly different binding affinities. And the task of the model is to predict the binding affinity so that the enantiomers in a pair are ranked correctly. Yeah, so if one enantiomer was better in a simulation, then it should be also doing better by in reception of a model. Okay, and the third one is basically pretty much the same, in some sense, the same task as the previous one when we want to predict chirality, binding affinity, but we are simply doing it by we are treating the same data set as a regression task. So we are not interested in ranking, but in overall performance. And here we have a set of results. Okay, so first of all, for that task, we didn't report the results. Okay, here we have two types of models, or three types of models. First is a kind of typical graph neural network. We have three of them, like GPS, spectral attention network, and very classical DMPNN. We have versions of the models with higher attacks. Yes, and we have the versions of the models, of two models, with our ChiENN layer. They are interchanging. As in GPS, the layers of transformer and GNN are interchanging. So here we replace the some default layer of GPS, GNN layer of GPS with ChiENN. And here we have models that are directly designed to be chiral aware. So it's hero, tetra, DMPNN, and ChiENN. Yeah, and here we have results. So it seems that using ChiENN instead of chiral tags is always better. I mean, except for the first task when the task was to predict the chiral tag.
Yeah. Well, why did you not look at the thing with text there?
Sorry, with what?
Like the task is to predict the text, right? And you have the tag symbol, so it should be completely trivial. It would be interesting to see, or one would hope that it's one now, and would be good to have that sanity check. No.
To check whether we can predict another tag, predicted by.
I just didn't. Why not put the number there?
Why don't? I mean, the numbers are ones.
Are they?
Yeah.
Did you run it and there are ones? Or
Yes.
Okay, good.
I mean, probably they should be put, but it's like, yeah. Okay. Okay, so anyway, the conclusion is that adding the ChiENN layer instead of tags improves the results for all the models, and also that, and by improves, I mean it also outperforms the Cairo model. I believe every setting of outperforms Cairo model. Yes, I think so, and also, like, using the ChiENN layers, standalone also outperforms the Cairo model. So that's pretty good. Okay, and we also performed kind of very short list of other experiments when we tried to choose our data sets that contains chiral molecules. And we choose two data sets that are kind of, I believe, well known. So, and the problem with those data sets is that they are pretty small. We have 1,000 molecules and 7,000, and there are not a lot of chiral molecules in there. However, there are some, and the results are not very conclusive, I would say. It seems that using chirality in any sense, whether with tags or with our ChiENN, doesn't improve the results of a model. for GPS and for spectral attention network. Yes, and it's yeah. So the evaluation, I believe, it's not particularly conclusive, except that using chirality doesn't seem to make an improvement. And I'm not really sure why. Probably it's because the chirality here is kind of irrelevant, maybe kind of noisy, and yeah, and I believe that one conclusion can be derived from that some more or much more experiments should be done to actually examine how important chirality is in the, let's say, casual tasks, molecular property prediction tasks. Okay, and I believe that's all. You have three. I believe it's not comprehensive lists, but you can find all the references in the paper. Yeah, so I believe that's all.
Okay, nice, very neat. Always good to think through some standard considerations for machine learning on molecules again. And it's still a bit mysterious why just having a chiral tag doesn't suffice. I guess that's kind. One could also say we could encode all our molecular structure in, for example, positional encoding of a graph, and then we have this type of positional encoding, and that should be sufficient. Like everything is, if you have some deep sets, or to just take sums all the time, or you have some transformer with the positional encoding, that should be sufficient. But we see that for these lower or for these data sets where we have lower amounts of data, it doesn't do as well as if we use message passing. And now here we're sort of, instead of just having the features, just having the positional encoding, just having the chirality tag, we're building the chirality into the message passing, and seems to help a little better.
Yes,
Yep.
true.
And is there anything else? Okay, good. Then I think there are no questions coming up, so we can stop it here. Piotr, do you have any last words? Any what are you doing next? Is there any particular use you see for this or something like that?
Any particular use of that model, or
No, that you want to try out next, or what you want to.
So probably I'm done with chirality. I guess I'm working with GNNs, which are, let's say, there are two layers of graph in GNNs, and I like graphs, so that's good to me.
Okay, let's talk about free-flow nets maybe a little more later. We have some questions, Denise and Mayank. So you want to unmute maybe?
Yeah, okay, let me start. I just wanted to ask if so if I understand correctly, the shift invariance in your network is simply achieved by basically a convolution, like a circular convolution, and the sensitivity to other types of permutations is achieved via essentially using a fixed-sized MLP. But this obviously is not ideal because you need to, again, it is fixed-sized. So for small world graphs, like real world graphs, like knowledge graphs, this probably will not be applicable because the degree distribution varies too heavily. And also, it is not clear to me how would you select like those edges that will fall into your edge budget, so to say, on each neighborhood. Although I guess it is like it can be done, but a little bit not robust, I think. So my question is, can we, instead of using MLP, use some kind of sequence model with well, positional encoding, or with even like an RNN with some positional encoding
Yes.
again, and so on.
Okay, so first of all, you can it's like you don't need to make that that window wide as a degree of a graph. Yeah, you can simply fix that degree, for example, to be k. You can set k equal to, and you will also be able to distinguish between the different permutations. It still holds, and then you can you have as you can have an MLP which is fixed size, but the size is not so big, so it probably is not an issue. And yeah, you can also use a sequence model like RNN here. I believe it's perfectly fine. I mean, it's permutation. It's not permutation invariant, so it should work.
Okay, and just to a very simple question: when you combine this layer with other non like layers that are not sensitive to chirality, are there some recommendations in what order to combine them and like so on?
We didn't test a lot of combinations. We simply use the, let's say, the most trivial one when we interchange the layers, like in GPS. Right, so my recommendation is I have no one.
Okay, thank you.
Yep. Hi, Piotr. Can you discuss a bit about the training details here, with respect to how many epochs and what were the hardware considerations like in like the compute used and so on?
That's a tough question. I don't really remember that. I can look at the paper. I believe it was rather a simple setting, probably 100 epochs. I was training it on, I believe, DJX. Like, I'm not sure which version. Okay, so sorry, I don't really remember the training details. I can check it out if you are really interested. I believe some of them are in the paper, like the, let's say, hyperparameters are, but the machine's details are, I probably need to check it out. Sure.
Okay, so for this kind of task, did you had to use additional compute as with respect to the other classical GNN tasks, or you had the same amount of compute that was necessary to utilize your training run?
Okay, so if you okay, so it's like the computational complexity does not really depend on the when you compare the computational complexity to the let's say standard GNNs. I believe the factor that makes the computational more expensive is the k number. Okay, so choose k equal 10, you will be roughly need to compute to perform like few times more computation than in standard GNN. But on the other hand, it's because it's like in a standard message passing network, you take one node and compute the embeddings for that node, and here you take few nodes and compute embedding for for those nodes, yes.
Mhm.
But the sliding window is pretty much of the same size. I mean, you have the same number of embeddings, yes.
Mhm.
But the size of the input layer for this MLPs, is
Okay.
multiplied by k.
No, nice. Thanks.
Okay. Okay, so
Good,
are
good.
there any questions?
Doesn't look like it. Then, Piotr, thanks for answering the existing questions and thanks for the neat presentation. And with that, I would like to say see you all next week.